Hello, welcome to our lesson on substitution. This is a method for solving certain integrals. We will derive this from the chain rule. So here's a reminder of chain rule. If I take the derivative of a function composition like this, where g of x is inside of f, then you take the derivative of the outer part, leaving g alone, and then you multiply by the derivative of g. So that's review. Now, what if we reverse this using integration? This means the antiderivative of this part is equal to f of g of x plus c. Now we're going to do something which will simplify this picture a little bit. We're going to substitute a variable in place of the function g of x, and that makes for a simplified integral. And this is why we call it substitution. We substitute the letter u in place of g of x. And what follows then, if we think about the derivative of u with respect to x, well, that's just g prime of x. And what I'm about to do now is kind of cheating, but for all intents and purposes, you can accept it. Du is g prime of x dx. Now I say this is cheating because I made it look like I multiplied both sides by dx, and that's not really what's happening, because du dx here, it's not literally some number du divided by some number dx. That's not what's really happening. However, this is still true, and we're not really going to get into the weeds on that, so just we'll roll with it. I'm just going to leave a little note here. The result here is still true. It's just that my steps kind of misleading. All right, so if I put all this together, then the integral I have above can be rewritten. Let's zoom out a bit. F prime of u is g of x, and this g prime of x dx is just our new differential du. And so we get a vastly simplified picture here once I've made a substitution with that new variable u. So this helps us solve a lot of new integrals, which is great. So before we start doing examples, I want to give a tip. When you encounter these problems, well, first you have to recognize that it's a substitution problem. And secondly, you need to decide, what should I make u? What should u be? And so for that, say try to find a function, quote unquote, inside, or it's an input of another function. And that's probably going to be a good candidate for u. It's my g of x, because we see up here, g of x is like an inside function in this picture. So typically, that's going to be a good choice for you. Sometimes an alternative approach is helpful. So alternatively, find a function that's rather on the outside, with an easy antiderivative, meaning the antiderivative is easy to find. And this could be a good choice for g prime of x, because g prime of x is on the outside here of this f prime part. So I would usually stick with the first tip I gave, look for an inside function, some expression that's inside a larger function, and make that your u. But sometimes the alternative approach is necessary. All right, so let's finally do a real problem here. Let's find all antiderivatives of 18x plus 1 times 9x squared plus x. That part is to the fifth. Now, in theory, you could technically multiply this out and then multiply by 18x plus 1. Then you would have a polynomial, and you could take its antiderivative that way. It's just that's not a very practical approach, multiplying this out 5 times. So instead, this is set up really well for a u substitution. So I have this inside function, 9x squared plus x, that's inside this to the fifth power bit. So I'm going to make this substitution, call that u. And when I make a substitution with this new variable, then I want my new integral to be completely in terms of u, not x anymore. So du, remember that's taking the derivative of u and then multiply by dx. So 18x plus 1 times dx. And this is our new differential du. And notice we have those pieces sitting here. Maybe I'll highlight. Got 18x plus 1, and I've got dx. And, well, that is du. And then this part is left, but that works well with our new u variable, because this is just u to the fifth. So u to the fifth du leads to a much simpler looking integral. So we do power rule on that. Don't forget the plus c. And now that we're at the end of the problem, we want to go back to being in terms of our original variable x. So now I'm going to plug in for u. This is 169x squared plus x to the sixth plus c. So we want to go back to x at the end. Right? It's a very powerful tool. Okay, let's find all antiderivatives of 2x times e to the x squared dx. So one way to tell that you are going to do a u substitution, besides the fact that we're in that lesson today, is if there's a lot of complicated stuff going on in the integral, that's a pretty good pointer that you want to do a substitution. So I have this x squared is like an inside function in the e. It's the input being plugged in. Notice I have the derivative of x squared sitting out here. So this is set up very well. If I make u my x squared, then du is 2x dx. And here we see you've got 2x dx. So those together form my new du. And this part is now just e to the u. So we get e to the u plus c. And now we go back to being in terms of x. So switching your integral over to being in terms of u is very helpful. Let's do a square root. And we'll use the letter t. Doesn't have to be x. So again, we want to look for an inside function to make my u. So perhaps 4 minus t squared. Now let's see what happens. Will we get a nice du that is compatible with this problem? And the answer is sort of. So for du, we take the derivative of u and then times dx. So I get negative 2t, or excuse me, not dx, I mean dt. Well, notice I don't quite have a negative 2 dt sitting in here. I'm close. I have a t dt, but not a negative 2 that's being multiplied onto it anywhere. So, are we out of luck? The answer is no. As long as this is just a constant, then we can work with that pretty easily. What you want to do is solve for the part that you do have using algebra. So I have a t dt, means I want to solve for t dt. So I divide both sides by negative 2. So this will get substituted in place of t dt. And I would prefer to write this as negative 1/2 du. All right. So my du doesn't have to perfectly match what we see in the integral. It's okay as long as the only difference is times a constant, like times negative 2. When that's the case, you can just rearrange things a little bit. So t dt, the part that we do have, will get replaced with negative 1/2 du. I'll go ahead and put that negative 1/2 outside. because you can do that with when you're multiplying by a constant. All right, and so then here we have square root of u, and finally du. All right, so square root of u is the same thing as u to the 1/2. So this will become u to the 3/2. I add 1 to that power and divide by that new power. And dividing by a fraction is the same as multiplying by the reciprocal. Oh, I forgot my plus c, didn't I? What really matters that you have it at the end, of course, but I like to write good steps here. All right, so these twos cancel. So I get negative 1/3 u to the 3/2 plus c. And now I would like to go back to my original variable t. So u is 4 minus t squared. All right. Next, let's look at the integral of x plus 1 times e to the 3x squared plus 6x. So as usual, I want to look for my inside function. It's a good candidate for u. This is getting plugged in into the e. So let's try it, see if it works. So I find what du would be, which is the derivative of u times dx. It's 6x plus 6 dx. And it might help if we factor out that 6, because notice I have an x plus 1 here. So if I factor out the 6, then x plus 1 is showing up now. So after I make the substitution, my new differential, du, is 6 times x plus 1 dx. Well, notice in the original integral, I have x plus 1 dx, but I don't have the 6. There's no times 6 sitting out there. Well, we can overcome this hurdle by solving for the part that we do have. So I take du divide by 6, or 1/6 du. So we can make that work. So this part I'm underlining, that is 1/6 du. And what's left is this e to the u. The antiderivative of e to the u is itself, plus c. And now we go back to x. So plug 3x squared plus 6x in for u. All right, next. We'll do a rational expression here. Antiderivative of x to the fifth over 2x to the sixth plus 5. So typically I've been saying we want to look for an inside function to be our u. Well, that's not really obvious here. There's not really a function sitting inside another, like some expression inside a square root or something. Well, we could just take a guess at u, and sometimes that works all right. But I want to point out that alternate tip I gave here. So we could find a function that is on the outside somewhere, which has a nice, simple antiderivative. And I wouldn't make that my u, but rather my g prime of x, so the derivative of u, essentially. So here, for example, x to the fifth, that has a pretty nice antiderivative. And notice we basically have an antiderivative of it sitting down there. That gives a pretty good indication of what I want my u to be. So I would still start at u, but it was helpful to think of the part that's in du. So it's still best if I make this my u, just this whole denominator here. Then du is the derivative 12x to the fifth times dx. So notice we don't have this exactly in the original integral because there's no times 12. I don't see a times 12 here. But that's no problem. We can just rearrange this. We do see x to the fifth times dx right up here. So we just solve for that. Du over 12. So it's 1/12 du. All right, so my new integral has a 1/12 out front because x to the fifth dx is being replaced by 1/12 du. And here we have 1 over u. So antiderivative of 1 over u is ln of the absolute value, remember. Now we go back to our original variable x. So u is 2x to the 6 plus 5. And one last thing. I'm not a huge fan of the absolute value bars with the ln. I mean, sometimes they're necessary, but in this case, they're really not, because notice that whatever number I plug in for x, I'm guaranteed to get a positive outcome. So we're taking it to an even power, and we're even adding a positive number to that. So the absolute value bars are actually doing nothing here, because what's inside is always going to be positive anyway. So I'm just going to get rid of those absolute value bars. Because they weren't really making a difference in this case. But you would have to take that on a case-by-case basis. All right, let's do a bit of a more challenging one. Well, I have a nice inside function there. The t plus 8 is inside the 6th power. So let's try that for our u. Okay, I don't really see another practical way to do this anyway. Like you could, in theory, multiply this out all the way, all 6 powers. It's just not very practical. So let's try doing a u substitution. U equals t plus 8. Well, then du is the derivative 1 times dt. All right, so du is the same thing as dt in this case. We'll notice that when we try to translate over to u, this part works well. I've got u to the 6th. And dt is just the same thing as du. But I haven't really dealt with this extra t here. And that's not good. I want to be in terms of only u, only one variable. So we need to do something about that t. So this is something we haven't quite done yet. We'll notice that if I look at the u formula, I can actually solve that for t, and I would get something reasonable. So since u is t plus 8, that means if you solve that for t, you get t equals u minus 8. So that was just rearranging this u formula up here. And now at first glance, it may not look a whole lot different from what we started with, but it's actually a lot better that this more interesting expression does not have the power associated with it, and we just have u to the 6th. That's actually easier to solve than having t plus 8 to the 6th. Because now I can just distribute this u to the 6th. So that'll be u to the 7th minus 8u to the 6th. And then it's just a simple power rule problem. So we get 1/8 u to the 8. And all right, here I have to carry my times 8 over, and I'm going to add 1 to that power and divide by that new power. And now we go back to being in terms of x, or excuse me, t. So u is t plus 8. So it means I've got 1/8 t plus 8 to the 8 minus 8/7 t plus 8 to the 7 plus c. All right. So that one was just a little trickier because once I made my substitution of u and du, I still had a t part that was left unaccounted for, but you could solve for it in terms of u. All right, let's do an extra challenge problem here. Let's use y. So y cubed times the square root of 9 minus y squared dy. Well, I am looking for a good inside function. Let's try to make that our u. And then du is negative 2y dy. Notice there's no times negative 2 out here, so probably going to want to move that over. I want to solve for y dy. Or negative 1/2 du. All right, well, notice that when I try to substitute u in again, we run into a similar problem to last time where I still have some unused things. Namely, okay, I'm replacing one of the y's here, but I'm still going to have a y squared left out of those three. So let's try to piece this together in terms of what we have. So well, we can certainly deal with the u part, that's the square root of u. And while we have a nice expression for y dy, that means I've still got a y squared left over. So how about we write that separately? And maybe I'll keep writing in terms of y for now. So here's that other y, I just separated it from out of the y cubed. So this part is the square root of u. Great. This part is nice. It's just negative 1/2 times du. Now we still have to deal with this y squared. But notice that that actually can be written in terms of u pretty nicely if we go back to the u formula. And we just do a little algebra to solve for y squared. So I don't think I'm going to write it out fully, but, well, okay, twist my arm. So y squared, if I add y squared to both sides, get y squared plus u equals 9. So then move the u over. There, so y squared is 9 minus u. And now we have our new integral in terms of u. So I'm going to write this negative 1/2 first, get it out of the way. Then 9 minus u times u to the 1/2, same thing as a square root, du. And notice I can distribute this u to the 1/2. And we'll get something we can work with. So 9u to the 1/2. So this is a u to the 1 times u to the 1/2. You add those two powers. U to the 1 plus 1/2 is u to the 3/2. And so now I can do power rule on each piece. All right, so get 9u to the 3/2 by adding 1 to that exponent. over 3 halves minus u to the 5 halves over 5 halves. Then we'll just throw the plus c outside. There's no need to write plus c in here. It would just get multiplied by the negative 1/2. And then you have a new constant c, or c prime, or some other letter, right? Just some other constant. So I'm saying there's no problem if you write the plus c just on the end. It's some constant out there. All right, so don't forget to distribute this negative 1/2. But let's maybe simplify these inner parts first. So I have 9 times 2/3 instead of divided by 3 halves. U to the 3 halves minus 2/5 times u to the 5 halves. And this 3 will cancel with the 9. Notice when I multiply by this 1/2, it's going to cancel both of those 2's there. So I'll be left with a negative 3, still have this 3 here. So negative 3u to the 3 halves. Now I've got a double negative here, and the 2's cancel. That'll be a plus 1/5 u to the 5 halves plus c. And now finally we can plug back in, substitute back, so that we get in terms of y again. So u is 9 minus y squared. So all that to the 3 halves plus 1/5 9 minus y squared to the 5 halves plus c. All right, we'll see you next time.